We're going on now to topic 2 of chapter 9 with only 2 topics left in this course after we complete this one. The objectives for this course are listed here, and we're also going to take a look at odds as it compares to probability. We'll start off by looking at the addition rules for probability and the probability of mutually exclusive events. Now we're going to look at cards here for a moment. And as we look at the cards, we have 2 events are mutually exclusive if they cannot occur at the same time. For example, if you were to select a card from a standard deck of 52, the 2 outcomes, the card is a jack. Well, these are jacks, and the card is a 7. These are the 7s. Now, the question is, are these events mutually exclusive? And the answer is yes. And the reason is you can't select a jack and a 7 at the same time. They are independent events. They're not connected. Now, in the second part of this, how about selecting a jack and a club at the same time? Are they mutually exclusive events? And the answer is no, because there are clubs that are also jacks. Okay, so that was a short one. Another background item is, let's consider the whole numbers between 1 and 20 inclusive. That means the 1 and the 20 are a part of the set. Event A, the whole number is less than or equal to 5. Well, there's that set. Here, the whole numbers are greater or equal to 17. There's that set. Now, would you consider these sets mutually exclusive? And the answer is yes, because none of the elements in this set are in this set. Okay. Now, if we're thinking of a Venn diagram for this, these sets would be a disjoint in the universe of 1 to 20 inclusive. And in this next slide, they're giving us a picture of it. So going on now to our next part of background. Here, sets C are whole numbers that are divisible by 3. And again, we're still dealing in that universe of 1 to 20, and we list them. And then here we have in set D, whole numbers divisible by 4. So are these sets mutually exclusive? Well, again, if you put the information into a Venn diagram, you see the 12 is common to both set C and set D. So these sets would not be mutually exclusive. All right, now for examples. In example 1, as we look at it, there are the sets A and C. Now, as we look at the solution as a Venn diagram, we see that 3 is common to both. So these sets would not be mutually exclusive. Continuing on to example 2, set B and set D. Are they mutually exclusive? Well, again, a Venn diagram really helps see this? And the answer is no. 20 is shared by both. Therefore, they are not mutually exclusive. Example 3. Determine whether the events are mutually exclusive. In one trial of a coin toss experiment, are the events getting ahead and getting a tail mutually exclusive? And the answer is yes, they are, because you can only get one at a time. Now, if you're shaking them together, two coins, that would be something different. But again, looking at the specific question. Now, for number 4, we have our deck of cards, drawing a 9 and drawing an 8. Are they mutually exclusive? And the answer is yes, because the 9s are separate from the 8s. Now, how about if we said drawing a 9 and drawing a club? Would that be mutually exclusive? And the answer is no, because a 9 is also on a club card. All right, let's go on. And they have a nice Venn diagram showing that they are disjoint set. Example 5. In one trial of rolling a single six-sided die, are the events observing a 2 and observing a 6 mutually exclusive? And the answer is yes. Now, keep in mind that we're talking about the number that comes up on top, because notice in this picture even you can see the 6 and you can see the 2. But in looking at a die, we think of the face surface that is up on top. So now in summary of what we've done so far, and you write this up, the addition rule for probability of mutually exclusive events is that it's the sum of event A and sum of event B together. That is the union. And again, we're thinking probability, so we're counting how often these events occur. Looking at example 6, finding the probability of mutually exclusive events. In one trial of rolling a single six-sided die, what is the probability of observing a 2 or observing a 6? Well, the 6 is going to be 1 out of 6, and then later the 2 is going to be 1 out of 6. So we add them together and get a sum of 2 out of 6, and then we reduce it to 1 out of 3 would be the probability. For example 7 now, we are looking at a deck of 52 cards. What's the probability of drawing an 8? Well, remember, there are 4 8s in a deck, so that would be 4 out of 52. And then if that one that you've drawn is replaced, drawing a 9. Well, these are mutually exclusive events, so it would be, again, 4 out of 52. Adding that up gives you 8 out of 52, reducing that to 2 out of 13. Now, this earlier part was pretty straightforward. Now we're going to thicken the plot a little bit. The probability of non-mutually exclusive events. So when we're considering the probability of these, since there is an overlap, there's an intersection of a member or some members, we have to be careful not to count these members twice. So in calculating, we'll need to note that. All right, so let's look at this example they're giving us. Here, event A is rolling a 2, and then event B is rolling an even number. Now, notice that a 2 is in the intersection because it's also an even number. So for something like this, we would say rolling a 2 and event B rolling an even number, you would need to be careful because as we look down at the bottom here, when we roll a 2, that would be 1 out of 6. When we roll an even number, that's going to be 3 out of 6. But we've already counted the 2. So what we have to do to properly figure this out is we can add the 1 out of 6 plus the 3 out of 6, which is 1/2 here, but we have to subtract the 2 that was already counted if we're using this one. So that leaves us with a total of 1 out of 2. And the reason for this, we can't count the 2 twice. It's already been used. They are not mutually exclusive. Therefore, you have to subtract that value that's already been counted. And we'll do some more to help illustrate this. Now in example 8, and I'll use my pen because this gets a little confusing here. Suppose we select a card from a deck. And what's the probability of drawing a diamond? Now, how many diamonds are in a deck? And that would be 13 diamonds out of 52. Now, or drawing a face card. Now, how many face cards? These are Jack, Queen, and Kings. And there's 4 suits, so that would give us 12 out of 52. But notice that 3 of these face cards here were diamonds that we have already chosen. That's what they're illustrating here in this Venn diagram. So since they are not mutually exclusive events, we have to subtract the 3 face cards that were already diamonds that we included here. And there's the calculation of this. So 13, 25, subtract 3 would give us 22 over 52, and that's going to be 11 over 26. All right, that I think makes it a little clearer. Here they're illustrating it, that the 3 face cards that are diamonds cannot be counted twice, so you have to subtract them. This is a good example of our rule here. Now they go through it in some detail. I think we kind of made it a little easier here. Now for example 9, we'll go up and look specifically. Again, you have balls numbered 1 through 20. You're randomly going to draw a ball. What is the probability that the number of the ball will be divisible by 3 or divisible by 4? So your first set is divisible by 3, and there they are listed. And your second event is B, divisible by 4. So as you look at these, you see the 12 is found in both. So in doing the math of it, and you're considering what you have, and we can look at what they have down here. So this first one's 6 out of 20 plus 5 out of 20 minus the 1 that's in both sets gives you 10 out of 20, which is reduced to 1/2. And I like the idea that they're showing us the Venn diagrams. I think that helps us tie in with what we've had in the past, and then showing us the events when they're not mutually exclusive. You can't have the doubling because this number was already included. Now, for background, we're going to take a look at what is called the complement rule for probability. And we can summarize it by looking at this Venn diagram. So here's our universe. There is set A. Now, what is A complement? Well, everything that's not in A, that's in the universe. So if you found that your universe is, let's say, 20, and in A there is 19, we can let the universe be expressed as 1, the whole, which is in a sense 20 out of 20. And if we subtract what A is, then what's left is 1 out of 20, which is our A complement, or the complement of A. So a little bit of background. We've done this before, but now we're using it for, in a sense, a shortcut to probability. And then the formal way to show it here is if we add what's in A plus its complement, that's going to equal the whole. And if we want to find the complement, we could take 1, which is the whole, subtract the complement, and that would give us what would A would be, or as the way I've illustrated it up there, would give us what A complement would be. So again, mathematically and in terms of probability, how it would be expressed and how they relate to each other. So now for example 10, I think which illustrates it very well. Here, an airport says that its flights are on time 92% of the time. So what would be the complement of that? Well, you would have the whole, subtract 92 from it, and then that would give you its complement. That is, 8% of the time, they're not on time. We'll be kind of thinking of this too as we go into our next topic, which is finding odds. Now, odds, something that's used in particularly racetracks where the odds for winning a race as compared to probability, and this is what we're interested in, is defined by, and I'll make it easy for you. Let's say the odds of something is out of 50, and you're going to win, let's say, 1 out of 50 times. So the probability would be 1 out of 50. This would be probability. How would you write that in odds? Well, odds are written 1 then of winning, but now you have to subtract that from the 50, in the sense, find the complement, and that would be 49. So when you add up the odds, that equals your sample space. And that's what they're describing down here. Okay, let's get an example. We're winding this. Now for number 11, we need to understand the roulette wheel a little bit here. And there's a European roulette wheel and there's an American. This is the American. It's a wheel in which there are 38 little sockets along the side here. 18 of them are red and they're randomly spaced. 18 are black and they're randomly interspaced as well. So that gives you a total of 36. And then there are 2 pockets that are green. And this would be like a 0 and a 0. Here, these are actually numbered. And again, depending upon the color and the number, eventually you get 38. So calculate the probability of a roulette wheel ball landing in a red pocket. Well, there are 18 pockets that are red, and there are 38 altogether, but they want the odds. So we have to subtract the 18 from the 38, and we would get 20. Now, this is the odds. That's not the probability. Now, we can often reduce that. We take a 2 out of each one. This would be, let's see, 9 to 10 would be the odds. Now here they're showing you the probability, but let's go down so we can see the odds here a little lower. And there it is, 9 to 10. Now, as we go on to other things, and I'll clear this up here, what's the probability of not landing in a red pocket? Well, again, if we subtract that from the other, it's going to be 10 to 9. That is the opposite of what we just had. And then the odds in favor of roulette ball landing on red, and that's what they've done here. Okay, so let's summarize this once again, and I'll go back to black here for this. So probability is out of the total universe, what is the possibility of an event? Now odds, you would take the event, subtract it from the total, and then list it as E to whatever remains in the universe, which is in a sense its complement. And if you reverse it, you might say this is a chance of getting red. What's the chance? What are the odds of not getting red? It would be just the reverse of that. And that's my little summary. All right. So in a race, and this is sort of a summary of what we've just said, if the odds are 1 to 8, what would be the probability? Well, it would be 1 out of 1 plus 8 out of 9. But to show the odds, you have to subtract that 1 from your universe to get, in a sense, the complement. And that's what they're showing down here. Now, this would be the formula. N is chance of winning out of the chance of not winning and winning. That would be the total of what you have. Now, for our last item in this, we're going to look at calculating probability given the odds. So here are the odds. What would be the probability? Well, our 3 stays on top, and now we just add the 2 together, and that becomes our universe on the bottom. And then to convert that to a decimal fraction, that would be 0.6. Okay, well, you'll be doing your certify after your practice in our classwork, and we'll see how you do. 2 more lessons.